Good day, everyone. In this work, we evaluate the stability criteria for the mimetic Runge Kutta methods. The numerical solutions of partial differential equations require spatial and temporal step size restrictions in order to guarantee numerical stability. The step size criteria ensures that the numerical solution does not exhibit spurious numerical instabilities that is otherwise not present in the physical system. And as we all very well know, these criteria are commonly referred to as the CFL condition or the Courant number. In this work, we derive the stability criteria for the mimetic Runge Kutta methods for the advection equation. We start with a brief overview of the mimetic methods. Mimetic discretization methods work on a staggered grid. The discrete divergence and gradient operators are set to mimic their continuum counterparts and are therefore said to be faithful to the physics of the problem. In particular, the Castillo-Grown mimetic operators satisfy a global conservation law, and in this case, it's the extended Gauss's divergence theorem, in order to achieve high-order approximations for div and grad. And the discretizations work on an inner product norm in the standard inner product with weighted matrices. If we consider the advection equation that is shown here, this can be discretized using a time derivative and a spatial form, which in this case uses a divergence operator, a mimetic divergence operator in combination with an interpolant matrix. It can be shown that the stability function for an explicit p-order Runge Kutta scheme is given by this polynomial term here, where z is a complex number. The advection equation that's discretized here can be written in the form of an ordinary differential equation, which is well known to have an exponential solution of the form that's shown here. As a result, stability can be guaranteed if the eigenvalues of the matrix A lie within the stability region, with the modulus being less than or equal to 1. We present here some of our results that we've noted thus far. What we see here are the amplification factors as a function of various wave numbers for CFL conditions. It can be noted here that for CFL conditions below 2, the amplification factor remains bounded and below 1 and therefore is unconditionally stable for all wave numbers. However, as the CFL condition goes above 2, we start seeing these contours of pockets where the amplification factor exceeds the modulus of 1, and therefore the system starts to see a numerical instability. Hence, it can be concluded that for the fourth order Runge Kutta scheme with a fourth order mimetic scheme, a CFL condition of 2.0 is where the stability criteria can be stated. It's more useful to look at the amplification factor as a function of CFL for various conditions and is therefore easier to plot it for multiple conditions at the same time. The plot on the left shows the eigenvalue stability analysis for a third order Runge Kutta scheme for using a second order, fourth order, and a sixth order mimetic scheme. It can be noted that in the case of the third order time integration with a second order mimetic spatial integration, the CFL condition is close to about 1.7. And as we start increasing the spatial order, the CFL condition starts to drop. The plot on the right is a similar plot for amplification factor versus the CFL condition, except that in this case, it has been plotted for a fourth order Runge Kutta scheme with a second order, fourth order, and a sixth order mimetic scheme. It can be concluded based on these plots that both the time integration order and the spatial mimetic integration order matter in terms of the CFL stability criteria. In conclusion, the stability criteria for the mimetic Runge Kutta methods have been presented for the advection equation in this work. The eigenvalue analysis has been implemented to derive the criteria for high order mimetic and Runge Kutta schemes. And we are currently focusing our efforts to extend these results for higher dimensions and for PDEs other than the advection equation. Thank you very much.